Very much, Marco. Thanks everybody for joining. Yes, also from my side, welcome to today's weather briefing. As Marco said, my name is Yasmin. My colleague is Andreas, and we are both working for the Austrian National Weather Service, the ZAMG. I am sitting in Salzburg while Andreas is in Vienna. As usual, this weather briefing will take about half an hour, and I will start with the actual weather situation in Europe. And this time I would like to put a strong focus on satellite images, and afterwards Andreas will continue and talk about a very interesting topic concerning the bandwidth of satellite channels. So, as usual, yes. As usual, please just quickly take the pointer and show me where you are. So I'm approximately here. Yes. So I think most of you already know that, just to get an overview. So we have in Scandinavia, Great Britain, Spain. So here we have over in Romania. Okay, yeah. Thank you very much. I'm also interested in who of you is probably new here. So maybe I might just clear everything. Yeah. Is there anyone that is joining for the very first time? So give me some sign. It would be nice. Okay, well, great. We have someone from Norway. Welcome then. So, yeah. Okay. So, all right. As I have already said, this time I would like to concentrate on satellite images and some useful applications, especially during winter time. So, I would like to start with the very basic one. Okay, the high-resolution visible satellite image. This is a satellite channel from 0.6 to 0.9 micrometers. It's from today at 10 UTC, and it's very interesting to observe movements in the clouds, to see the clouds, to see some structures, also to see more or less some land structure, but we do not have any information during night. So for example, this is from today 7 UTC. We do not know what's going on if it's dark. That is something that affects us all year long, but especially in wintertime, if you go to your shift at, let's say, 5 or 6 in the morning, and you do not see anything on the satellite image, that can be a problem. We have something that might help in this direction, that is the infrared satellite image that also shows information during night. Here we also see lots of cloud structures, but still we have limited information. We do not know so much about different cloud layers. We do not know anything about the soil properties, maybe the cloud phase, I don't know, the types of air masses and all that stuff. We just see some movements, and yeah. This is also from today 10 UTC, so one can already see some denser clouds here, and also here is a cloud band. Maybe most of you know that there is a high pressure approximately in this area. We have here the cold front and the warm front here, an occlusion, or 1, 2, maybe even 3 low pressure systems over here, but we want to find out more about it. So if we move on, well, before that actually, I want to say that yes, at the moment, in this time of the year, not only darkness can be challenging, but also, for example, snow at the surface, or for example, fog is also a very important topic, at least in Austria at the moment, and there is one way to help out: the RGB satellite images. So Meteosat second generation satellites, MSG satellites, provide 12 channels in different wavelengths, which can be combined to create colorful images for different purposes. I think most of you know it, but just for those who are new maybe, those images are called RGB because each wavelength can be assigned to either red, green, or blue in order to create those colorful and meaningful images. I will go through a couple of RGBs to illustrate some advantages and disadvantages. So I want to start with a quite simple one and easy to understand, the day natural color RGB, also the day in the morning at 10 UTC. And so something, we have some additional information now. We can distinguish different soil properties, for example. So we have some desert soil. Here we have the green, the vegetated areas. Also here were Great Britain, very nice to see. And also we can distinguish between kind of different cloud layers. The cyan-colored clouds, for example, those here are ice clouds, and the white, bright white cloud structures are water clouds. Here, for example, the three channels, channel 1, 2, and 3 are combined, which is the visible 0.6, visible 0.8, and near infrared 1.6 channel. All right, so here now we still have the problem that during night we do not see anything, and we also have the problem that it's very difficult to discriminate between snow and ice clouds, because here, for example, in the Alps you can see the snow-covered land, but the high and thick cold ice clouds have almost the same color. So we might think about something else we can use here. Concerning the problem with the night, we could have a look at the, okay, I have a small question for you. Let's do that before. I have marked this small area, and just take again a marker or something and try to find out which of the following things you can see here. Is it snow-covered surface, ice cloud, water cloud, or fog? So yes, I think that most of you probably know, and also of course I have said it just to check. Yeah, everyone is awake. Thanks. So now we can go on. And yeah, as I have said, during daytime it's very useful to look at another RGB, the 24-hour microphysics RGB. This one is also from today in the morning, and here as well we can distinguish between the ice clouds and water clouds. Ice clouds are the dark red structures, like here and here, and water clouds are a more yellowish, like over here and also in these regions. It can also be fog, of course. Yeah, okay. This image is very good for detecting fog, day and night. And it's also quite interesting for detecting high and thin cirrus clouds. Yeah, this is just an example for 8 UTC, so you can see there is no difference or no disadvantage during night. Again, I have prepared 3 small tasks. So where do you think on this picture? It's not from today, it's any day from the past. Where do you think is fog or low stratus? Do we have any guess about that? Yes, Lucas. Yes, Milana, very good. There is some smaller area in northern Italy with fog. Yes, and of course this region is low stratus fog. Yeah, that's right. Thank you. Then let's clear that again. Thanks. What do you think is thick, high, and cold ice clouds? Yes. Yes, all right. You have paid attention. That's very nice. And cirrus. Let me just clear our pointers again. And that's okay. And here we have the cirrus. Yes, exactly. Okay. Thank you very much. Just because I think it's quite interesting or nice to see, if you see here south of France, above the ocean, we have this very interesting structures like a net that's probably some leftovers from condensation trails of airplanes here. All right, so we have now something that we can look at day and night, but still we cannot clearly identify snow-covered surfaces. And for this, I want to go one step further. Okay, so let's have a look at the day microphysics, RGB, also at 10 UTC, and this is very useful not only to see big ice clouds, the orange structures here, but also some structures at the ground. Like here, you can see the Alps that are pink, and that means there is snow at the surface. Yeah, cloud-free land and oceans are blue. You can see that all over here. And then we also have this apricot color, like here. That means low to mid-level water clouds. Right, what do we have here? Okay, snow-covered surface. So the Alps are now covered by some clouds. Where else would you detect some snow-covered surface? Do you have any? Yes, in Norway, yeah. Yeah, that might also be some. Okay, perfectly fine. Thank you very much. All right. One last RGB. No, it's not the last, but another one is the fog RGB. That's also very useful now when we have some fog, and especially if we have small areas of fog in an alpine valley, for example. I want to show you an example from today in the morning. I zoom in into this area. It's pretty cool because the resolution is very high, so I can zoom in here and I can actually see that here, just a little bit south of the city of Salzburg, we have two valleys filled with fog. And for example, also yesterday in the morning, we had some fog in some valleys, and that was really nice to detect by the fog RGB. So here we have also two webcam images. Last but not least, the air mass RGB, that is nice to look at all year long and day and night. It's just very beautiful to see the bright cloud structures, the white clouds that are high level thick clouds. And in blue you can see the polar air mass, which is ozone rich. The green colors is warm tropical air mass, ozone poor. And then we also have the red colors, like here and here or here. That means dry air masses. So usually it's subsiding air from above, or it also indicates PV anomalies, cyclogenesis, and that things. All right. I think I'm done with that. So I pass the microphone over to Andreas.
Thank you, Yasmin. Now let's come to another topic. Welcome everybody. My name is Andreas and I have the second part of this presentation. I want to talk about satellite channels, and I called this presentation Some Considerations about Central Wavelength and Bandwidth. So usually we are used to call the spectral bands from satellites, from severe instruments, for example, 10.8 micrometer or 6.2 micrometer for the water vapor absorption channel. So we most of the time always talk about the central wavelength, and we do not so much think about the bandwidth associated to these channels. And I want to tell you now and show you that the bandwidth is also very important in relation to the satellite channels. So how did I come to this topic? During the summer, I think most of you know ePort. In fact, it's ePort Pro. You know that there are a lot of satellite images, and during the summer, I included the Himawari images. This is the Japanese geostationary imager, and I tried to include the single channels like 10.4 micrometer. This is the infrared channel. For MSG, it's 10.8, so it's not exactly the same. Visible image 0.86. For MSG, it's 0.8, so it's very similar. Water vapor is the same, 6.2. And I created also some RGBs. I will take my pointer here. Here are the RGBs. You can have a look at them. And while programming the recipe, I saw that for the night microphysics, for this one here, there is some difference between the MSG and the Himawari night microphysics. So I have here an example. You clearly see Meteosat 8. This is the first satellite of the second generation, which is now positioned over the Indian Ocean. But there's an overlapping to the Himawari area or scanning area. And you see that these are the same clouds, one time seen from Meteosat 8 and one time seen from Himawari. And you see that the Himawari image is different. Sure, the recipe is the same, some slight modifications for the temperature range, but nevertheless you see that the Himawari image has lots of small yellow dots. So, and I was wondering, where are they coming from? And this is quite obvious. I think most of you know why this happens. This happens, by the way, also for the Meteosat 8 image, but only for very, very low temperatures in winter with very, very cold surfaces, but not for cloud tops you can find in the satellite images. These are not cold enough to create such artifacts in the image. But for Himawari, you have this. And for Meteosat 8 and all other Meteosat generation satellites, you don't have this. So, this is the recipe. I took it from the recipe guide from the EUMeTrain page, and you see here you have the 3.9 micrometer channel, and this one is responsible for this noise. Yeah, but this still does not explain why Himawari has problems and MSG does not have problems. But the noise obviously comes from the 3.9 micrometer channel. So, it is well known that this channel has problems with very cold temperatures, because this is a very known slide from a EUMeTsat presentation. You see that for very cold temperatures here, I hope you can see my pointer, for very cold temperatures, a slight modification of the radiance, the radiation emitted from the Earth, leads to a very strong temperature change. Here the temperature and the x-axis, because for very cold temperatures at 3.9 micrometer, the radiation is really, really small. Not so for longer wavelengths. Here you have the 10.7 or 10.8, nearly the same. The curve is much steeper. That means a change in radiation on the y-axis will result also in a small change of temperature. But here again, For the 3.9 micrometer channel, a very small variation in the received radiance, we speak of milliwatts per square meter, will lead to a very high change in, or big change in temperatures. This is because the amount of radiation in this wavelength, this is the radiation emitted from the Earth, of course, during the night, not during the day, only during the night. And we have also, that's what you see here, these dotted lines. The radiometer is not very exact. There is the precision of the instrument is plus minus 0.0086 milliwatts per square meter. So there is some problems, there's some variations in the measurements, and these small variations lead to big temperature changes, and that's why we have this yellow dots, this big differences from pixel to pixel. But this still does not explain why MSG has not the problem at the same temperature and Himawari has. So let's go on. Oh yeah, here it shows a small variation again in the received radiation leads to a big variation of the temperature. So here you have the Himawari 3.9 and the MSG 3.9 micrometer channel. In fact, for Himawari it's 3.88, but the difference is not very big. And this is the central wavelength. So this graphic here below this table shows you how the instrument works. That means it shows you some kind of sensibility curve, and the central wavelength indicates the most sensible reaction from the sensor at a specific wavelength. So for Himawari and MSG, it is around 3.9 micrometer. When the sensibility, the intensity of the radiation is only half, it's 50%, then we have the lambda min and the lambda max. These are the this is the called full width at half maximum. This is what is often used to indicate the bandwidth of a sensor. And you see here, this is very important. You see here, I mark it in green, the Himawari channel 3.9 has a very, very narrow bandwidth, while MSG has a very broad bandwidth. And this is the reason for the difference, and I will explain why. So this is the Planck's law, you know that. Here a little bit special because it's in a double logarithmic graphic, but nevertheless, the colder the temperature, the radiation, the lower this curves, and here is approximately the Earth with 300 Kelvin, and this is the Sun with 5,800 Kelvin. Here you have a maximum in the visible range, and the Earth, of course, there's no visible light emitted, but long wave radiation. Here we have the 10.8, and 10 micrometer is the highest intensity. And the this is 2, 3, 4, 3.9 is about here. Here's the 3.9, but for 300 Kelvin, and this is quite a warm surface, we are talking about colder surface. So for colder surface, there must be some curve like this here. And you see that the amount of radiation for very cold surfaces is small. So let's have a look at the bandwidth. And this is the same graphic again, but showing you the different bandwidth. In blue, Himawari, very narrow, and MSG, a broader bandwidth. And you see this graphic is not well drawn because, in fact, the MSG bandwidth is 4 times the Himawari bandwidth, and this is not the case in this graphic. But sorry, I did not succeed in drawing it better. Anyway, what happens? Himawari gets radiation in this small area only, while I change the color, while MSG gets it from all this broader band. So the sensor, the MSG sensor, gets much more radiation intensity, much more watt per square meter than the Himawari. This is the big difference. So the sensor gets much more energy from the Earth because the band is broader compared to Himawari, which gets much less energy and has therefore problems to resolve the temperature. So the question is a broad channel width always better? In case of the 3.9 micrometer channel, it seems that the broader channel is better for the instrument. It gets more energy and can better resolve the temperature. But what you can see here in this graphic is, again, the ideal curve of the Planck black body curve of the Earth, 300 hectopascal, 300 Kelvin, excuse me. And then you have the real emitted radiation here in yellow to this curve. And I want to draw your attention on this part here, the O3 absorption. So when energy is absorbed by the atmosphere, the satellite measures much less radiation. And this is the case here. So the question is, why not have always broadbands for satellite channels? Seems to be an advantage, especially for very, very cold surfaces. But then we have another problem. Yeah, again, this marks the area where I want to focus on. We have another problem, and this is this graphic here I want to show. Here, this is just a schematic, and it shows again the ozone absorption, but don't take it for real, it's just a schematic. If you will have a small channel width, for example, this ochre yellow band, we receive radiation really only from this absorption region. If the bandwidth is larger, for MSG, for example, then we get radiation outside the absorption band. Here, for example, and here. This is not absorbed anymore by O3. So what happens? A larger bandwidth will blur the image. If we have a small bandwidth, then we get much precise information, and the spectral resolution, that's the technical word, the spectral resolution is much higher. So this leads me to my conclusion on the considerations about the central wavelength and bandwidth. 3 conclusions. Sensors with channels having the same central wavelength can often show different temperatures if the band is different. That's what you have seen in the first image of the night microphysics RGB, two different temperatures. A large band width can be beneficial in case of small radiation intensities, because the sensor receives more energy from the Earth. And but on the other side, the disadvantage is when scanning the Earth's radiation in absorption bands, because a narrow band has a better spectral resolution. So you will better see the absorption bands if they are very narrow. So it depends what you want to have and which region of the spectrum you look at. Sometimes it's better to have a narrow bandwidth, and sometimes it's better to have a bigger bandwidth. So this is so much about the considerations. And I have to add now, there is a special day today. What happened 40 years ago? We have a celebration today, and it's really a chance that we have the weather briefing on this day. Meteosat, the first Meteosat, the first geostationary satellite of EUMeTsat was launched exactly today in 40 years ago. And this is the reason why we have to celebrate today with a nice birthday cake. And I give back now to Yasmin. Thank you.
Thank you very much, Andreas. That was very interesting. I hope you can hear me now. If not, tell me. So basically, we are at the end of our presentation. Thank you very much for your attention. Just one last thing, an invitation to all of you. There will be the EUMeTrain event week, which is taking place twice a year. And this time it is about the topic warnings. So it's all about warnings with a special focus on effective warning methods and communicating warnings, and it will take place from 11th to 15th of December. It's online, and you can register via this link. Maybe we will post it also in the chat box so that you can directly go. All right. It's highly recommended to take part. You can also take part for just 1 or 2 days if you don't manage the whole week, but have a look at it. Okay, the second thing is we have an evaluation survey going on, so please, after this weather briefing, go to this link and just just fill it out. It's a short feedback for us. Please also do it if you have done it before. Yeah, thank you very much for the links, Marco. So you can find both the links now in the chat box, and there is also the announcement for the next weather briefing, the so-called Christmas weather briefing. This time done by Vesa Nieto-Schwara from EUMeTrain, and it's taking place on 14th of December at 1:30 UTC. Thank you very much, and I give the microphone back to Marco.